Hello. Today we're going to talk about Le principle. Um, we're going to spend a couple days doing this because it is really tricky. So if you feel like after today you don't have a single clue what I was talking about, that's fine. Hopefully after tomorrow's lesson you'll feel a little bit better. So we're just going to get started. I shared a 4-minute clip of a guy going over, Professor Dave, I think his name is. That might help too, to get a different way of listening about this topic. Just throwing that out there. I would watch it. Okay, so I'm gonna get started and just try to do your best. Oh, before I start, one thing I wanted to mention, so in terms of like a dynamic equilibrium on the homework, so one of the more frequently missed questions was does a reaction occur always in one direction, always in both directions? So basically there's some reactions that occur only in the forward direction. Like if you burn a match, that is the only way it can go, but most reactions can go back and forth. The other thing was, it was asking about the rates. So when you're going forward, reactants to products, the rate is pretty fast at first because you have lots of particles that are bumping into each other, and then it slows down as you have less of those, as the reactants get used up. And then likewise, going reverse, you have zero product at first, and then you keep making more and more, and as you make more and more, the reverse reaction gets faster because they're bumping into each other more and more. Okay, so that was just a recap of what I saw on the homework. You are going to have homework on this topic, but it won't be till tomorrow. Okay, so let's get started. All right, so this is Le Chatelier's principle. So it says if a system at equilibrium is disturbed by either a change in temperature, a change in pressure, concentration, sometimes volume, if we're talking about pressure, the system will shift its equilibrium to counteract that effect. So basically, like if you are a man or woman walking on a tightrope and you're balancing and the wind blows from one direction, you have to shift in the other direction to counteract that stress. So that's basically what this whole topic is, but it tends to be really wordy and confusing. So we'll just do our best. Okay, so you're gonna encounter some words that are just different. So the first word you're gonna hear a lot is stress. And this is any change to the equilibrium conditions. So a change in pressure, temperature, concentration. All right, next you're gonna have the word shift. The direction a reaction will proceed, either forward or reverse, to make up for the change in equilibrium. So I'm going to talk about stress, and I'm going to say, okay, based on that stress, the reaction shifts to the right or to the left. So when it's going forward, the reaction is shifting to the right, and when it's going in the reverse direction, it's shifting to the left. And so you're just going to write, we could write forward or reverse, but it's easier to write right or left. Okay, and then the next word you're going to hear is favor. And when you shift in a certain direction, that means it's favoring that direction. So if I'm shifting right, I'm favoring the products, which means I'm making more of the products. So the direction a reaction proceeds will either favor the reactants, meaning it'll make more reactants, or it'll favor the products, meaning it'll make more products. Okay. All right, moving along. All right, so let's try to draw a picture of this reaction, and I'm just going to make up the flying through my face. Make up the numbers as we go. So N2 is going to look like that. It's diatomic, remember. So is H2. And then ammonia, NH3, is just going to have an N with 3. So I'm not going to worry about showing things that are balanced. I'm just going to draw a picture with a bunch of stuff. Okay, so let's draw maybe like, I don't know. We can draw like 4 N2s. And then we can draw 3 H2s. So we're just looking at like a snapshot picture of what it might look like. Okay, and then that one's not very good. Okay, and then we're going to draw NH3. So let's draw a bunch of those too. 1, 2, 3. So that's 1 NH3. 1, 2, 3. There's another. And your final one. Okay, so this is the original picture. This is our equilibrium. So when it's going back and forth, this is what we had. So the first stress I'm going to do is I'm going to add extra H's. So I'm going to draw the addition of 3 H's. Okay, so at this point, I stressed my equilibrium, and my reaction is feeling like there's too much hydrogen. So it wants to shift in a way to use up the extra hydrogen. It doesn't want that extra hydrogen to be there. So now I'm going to switch colors and just kind of show you what'll happen. So when it tries to get rid of this extra hydrogen, the way it's going to do that is by reacting with N2. Okay? And when I react with N2, I end up making NH3. So basically, I need 3 hydrogens and 1 nitrogen to make a new NH3. Okay? And then I have 3 hydrogens left. So I want to get rid of those 2. So the way to do that is take those 3, and they're going to react with another nitrogen. So I've produced 2 new ammonias. So let's just recap. My reaction felt like there was too much H2, too much of this stuff. So it needed to shift in a way to use it up. So the way it uses it up is if these 2 react together to make more NH3. So let's just draw the remaining pieces. So I have 1, 2, 3 N2s now. I still have 3 H2s. And then I have 1, 2, 3 of the original NH3. Okay. So what happened to the amount of N2 as we go from the original to the new? So in the original, I had 1, 2, 3, 4 N2s, and now I only have 1, 2, 3. So as I proceeded to the right, the amount of N2 went down, decreased. and what happened to the amount of NH3. So in my first one, I have 1, 2, 3 NH3s. And in my next one, I have 1, 2, 3, 4, 5 NH3s. So from here to here, the NH3 went up. Okay. So now we're going to put it into a rule. Okay, so here's the rule. If you increase the concentration, the reaction is going to shift in a way to use up what was added. So in the reaction above, the thing that was added was being added to the left side. So since it was being on the left, it was adding to the left side, the way to use it up was making the reaction shift to the right. So to use up what was added always shifts away from the addition to the opposite side. So if I add something on the left side of the arrow, it shifts to the right. And if I add something on the right side of the arrow, it shifts to the left. Okay, if you decrease the concentration, the reaction shifts in a way to make more of what was removed. So the only way it can make more of what was removed is shifting in the direction of the removal. So it shifts to the same side as what was removed. So if I remove something on the left, it shifts to the left. And if I remove something on the right, it shifts to the right. So we're going to go through and we're going to do the shifting first, and then we'll fill in all the boxes after. Okay, so this is how I set it up. This is not necessarily how you will see it on a question. All right, so first thing you do is draw a line through the arrow, and I have bolded this going all the way down as a separation point. If you have trouble with left and right, left and right. Okay, so I shade in what was stressed because I'm not going to really worry about that. So I'm just showing you the position of the stress. So if I add CH4, so I increase CH4, that's my stress. My reaction feels like too much CH4, I need to use it up. So if I look at my rule, if you increase the concentration, it shifts to the opposite side. So since I increased on the left to use it up, my reaction shifts to the right. Okay, so same idea. On this one, I'm adding CO2. This time CO2 happens to be on the right. So my reaction feels like, wait a minute, too much CO2. I need to shift to get rid of it. So I need to shift away from what was added. So in this case, I'm shifting left. Okay, so if I increase on the left, I shift to the right. If I increase on the right, I shift to the left. Removing is the opposite because you want to make more of what was removed. So if I remove O2, I'm decreasing it. I want to make more of that. So my reaction feels like I don't have enough of it, so I need to point my arrow or my shifting in the same direction. So when I remove O2, since I'm removing on the left, I shift to the same side, left. Okay, and then if I remove CO2, right there, I've removed on the right, so I don't have enough stuff on the right. So I'm going to go in that direction because these two things are going to react and make more. So I'm going to shift to the right. Okay, so the next thing is, what do we do with all these extra boxes? Okay, so if I'm shifting to the right, I have reactants and products. This is a right-hand shift. I'm going to favor everything on the right-hand side. So when I favor everything on the right-hand side, that means everything on the right goes up and everything on the left goes down. Okay, so in the first one, I shifted to the right, meaning I'm favoring the products. So these will increase, and then any extra boxes you have on the other side will decrease. So really, if you don't understand this at all, whatever way your arrow points, the stuff on that side goes up. So if I shift to the left, I'm favoring everything on the left-hand side. So the stuff on the left goes up, while the stuff on the right goes down. So this time I'm going left, so everything on the left goes up. Do that side first, whatever way it's pointing, and then anything on the other side goes down. Next one, shifting left, so in that direction, everything on the left goes up, and you ignore any boxes that are shaded in. And then the other side, empty boxes decrease. Okay, on this one, I'm shifting to the right, so the stuff in the empty box will increase, and the extra boxes will decrease. Okay, so let's just do one more, since you don't have any homework with this. Okay. Okay, so temperature is going to be similar to concentration. You want to think about heat as either a product or a reactant. So an increase in temperature, your reaction feels too hot. So it will shift to use up the added heat. This always occurs. So if I'm using heat, this is endothermic. A decrease in temperature shifts to make more heat. This always occurs in the exothermic direction. I almost never think about the endo-exo thing unless they ask me about it. I just do it according to where heat is. So they don't tell you where heat is all the time. They give you your delta H, which we learned about last unit. So since my delta H is negative, I know that means it's exo. And since exo means heat is released, I know that heat is a product. So I'm just going to write plus heat on the product side. And now we'll go through, we'll do the shifting first and then the increase decrease next. So I'm going to pretend this is actually a box over here where I can write down what's happening with heat. So I'm increasing temperature. So I'm increasing heat. So it's kind of like you're increasing on the right. So it needs to shift to get rid of it or get away from it. So I'm increasing my heat here. So I'm going to shift left. Okay. Likewise, if I decrease heat, it's just like what we did on the last page. You shift towards the decrease so that you can make more of it. So it needs to get hotter. So I'm going to shift towards the word heat to the right. Okay. So remember, if you have a right-hand shift, the stuff on the right-hand side goes up, while the stuff on the left goes down. If I have a left-hand shift, the stuff on the left goes up, while the stuff on the right goes down. So I'm just going to add that into these boxes. So I'm shifting left. So I look here. Oh, everything on the left goes up. So everything I'm pointing at goes up. Increase, increase, decrease. I'm shifting right, so this has to increase while these have to go down. Okay, so we'll call it a day for that, and then tomorrow we'll finish. There's one more shifting really, and then we're gonna do a bunch of practice problems, and then you'll have a homework. Okay, so that's it for today. See you later.